Here's a little demo of eigenvalues and eigenvectors. An eigenvalue tells you how something behaves. An eigenvector tells you what behaves that way. For example, let's consider the 10-stage RC filter in the lecture notes. It has, in state space, an A matrix, which is negative on the diagonal, 10 on the off diagonals. The transfer function has the dominant pole at minus 0.42 and 9 other poles. The eigenvalues are the same as the poles. If you notice the transfer function, the poles up here are exactly the same as the eigenvalues. That tells you how the energy decays in the system. The eigenvectors tell you what behaves that way. The fast eigenvector is on the left, the slow one's on the right. So let's do a computer simulation in MATLAB. Here I'm going to take the dynamics I'll give it an initial condition, have the input being 0, and let it run. At any given node, the change in voltage is your minus 20 on the diagonal, 10 on the off diagonals, except for the last node, and let it run. Suppose I excite just the slow mode. So turn up all these initial conditions and turn on this one. Let's let that run in MATLAB and watch what happens. I gave it an initial condition, and the shape is staying the same. The eigenvector, there's only one eigenvector excited. That mode shape remains constant. The amplitude of it is decaying exponentially by its eigenvalue, e to the minus 0.43t. That's the slow mode. Control C to get out of there. Suppose instead I excite the fast mode. Let that out. You have to watch this quickly. You're gone. The fast mode has a pole at minus 39. Doing that again. This shape stays the same, just decays as e to the minus 39t. If I give it a random initial condition, like so, what you're going to see is initially all 10 eigenmodes are excited, and it gives you your initial condition. Fairly quickly, the fast modes all decay, and all you're left with is the slow dominant mode, the first one that we looked at. So if we throw that in MATLAB and let it run away in the simulation, here's the initial condition. Eventually the fast modes die out, and there we are left with the slow mode at minus 0.43. That's why we call those dominant modes. They dominate the response after a short time.